In this video, I'm going to demonstrate how to perform a Friedman's ANOVA, which is the nonparametric alternative to the repeated measures ANOVA. In this case, what we're trying to do is compare multiple time points to each other to see if there are significant differences on a single outcome. But in this case, as compared to the repeated measures ANOVA, we're either working with ordinal scale data or non-numeric data, non-normal numeric data that we want to compare. So in this case, what we have here are some outcomes that were measured after an intervention. And we measured the score on this outcome immediately after the intervention. And then we want to compare that to a 6-month follow-up and then a 1-year follow-up. So we've got 3 time points we want to compare. We can compare more than 3 if we like, but typically the Friedman's ANOVA is used for 3 or more time points that we want to compare. And so in order to do that analysis, we want to go to the Analyses menu, and we want to find Friedman, and that's our decision box. So our null hypothesis in this case for a Friedman's test in this example would be that the median score for time point number 1 will be equal to the median score for time point number 2 will be equal to the median score for time point number 3. And so the test will do an omnibus test first to see if there is significance somewhere among the groups. And if it discovers that there is, if that's significant, then we would do a post hoc test. Because we're doing post hoc tests, they aren't accounted for as far as the error rate. So we'll need to do a Bonferroni correction to adjust the p-value for doing our post hoc tests. And so we can change that here in the options menu. And so you can see here the alpha level we're using for the omnibus test is 0.05, which is appropriate. But if we've got post hoc tests, we can adjust the alpha level at which the post hoc tests are performed. And so since we have 3 pairwise comparisons we may do, we would take that value and divide it into the initial 0.05 alpha level. And that would give us an adjusted alpha level, 0.016. So that's the alpha level at which the post hoc tests are going to be performed, and then we need to use that then to determine if the differences we're seeing among the groups is significantly different at this adjusted p-value. So once we've entered it, and that's going to be different depending on how many pairwise comparisons you might have. So if you've got 4 time points, that's going to be a different number of pairwise comparisons and then a different alpha level. So once we've entered that value in, we can go ahead and save options, click the close button, and now we want to indicate to Intellectus which time points we want to compare. So we go ahead and click under the variable option, click add modify, and we're going to work with post-intervention time point number 1, time point number 2, and time point number 3. So once we've selected whichever number of variables we want to compare, we click confirm, and then we click calculate. And so what we're going to be doing here, again, as I mentioned, is we're going to be looking first at the omnibus test to see if there is a significant difference somewhere among the 3 time points. So we're going to go to the raw output here and take a look at that. So we're looking for this piece of information between these 2 tables, and this is the actual chi-square result as part of the Friedman omnibus. And we can see here the p-value is quite a bit below 0.05. There's 5 zeros in front of the 1 here, so it's 0.000001. So that's quite a bit less than 0.05. So we have a significant omnibus test here. So that means we can move on to the post hocs. And you can see how it's arranged in the table below. We're comparing time point 1 to time point 2, time point 1 to 3, and 2 to 3. So how we assess these potential differences is we have a critical value here, and we're going to compare that critical value to the observed difference. And if the observed difference is greater than the critical value, then we can say that those 2 groups are significantly different from each other. If that value is less than the critical value, then we cannot say that there's a statistically significant difference between those 2 groups. So let's look at our first comparison here, time point 1 compared to time point 2. We can see the observed difference is 7, which is not greater than the critical value. So that indicates that time point 1 is not different than time point 2. As we look at point 1 compared to point 3, we can see the observed difference is greater than the critical value, so the difference between these two groups is significant, is we look at 0.2 compared to 0.3. We can see that the observed difference is also greater than the critical value. So the difference between time point 2 and time point 3 is also statistically significant. So that it appears the change over time from point 1 to point 2 is not different statistically, but when we get from point 2 to point 3, it is different. And then overall, the change from point 1 to point 3 is also statistically significant in its difference. So we want to make sure when we're reporting these results, we want to report the median value for each group. So we have to run descriptive statistics to find out the median value for each time point. And then, of course, we'll report the p-value, the chi-square value, and then report the results of the post hoc using the adjusted p-value using Bonferroni correction. And then we can also determine an effect size value for these pairwise comparisons, and we'd use the same formula that we would use for the Kruskal-Wallis test or the Wilcoxon signed rank test. So hopefully you found this video useful, and good luck using it in your own research.